The calculations that we've been learning to do in this worksheet are important because they help us analyze unknown solutions. In particular, we can find the concentration of an unknown solution using the same calculations that we did in the last video. For example, suppose I've got sulfuric acid, which is battery acid, and I want to find out what its concentration is. One way to do that is to react it with base solution, like sodium hydroxide. Now I'm going to get out of this. Sodium sulfate and water. And if I balance this, I can see I need a 2 here and a 2 here. So we'll just do that really quick. Here's a reaction. And suppose I have 25 milliliters of H2SO4, and I want to know what's its concentration. Now what I can do is drop some sodium hydroxide solution onto that 25 milliliters until it's completely neutralized. So suppose I have some 0.100 molar sodium hydroxide solution, and suppose I drop it on top of the 25 milliliters of H2SO4 until I see the reaction is complete. Suppose it takes, I don't know, make up a nice round number, 10 milliliters for that to happen. Let's keep everything at 3 significant digits here. So how do I find the molarity of the sulfuric acid from these 3 numbers? All right, well, let's think about what we want. It's a unit conversion problem. I want the molarity of the sulfuric acid, but I'm not going to write capital M H2SO4 over here as my target. I'm going to write what a molarity is. I want how many moles of sulfuric acid I have per liter of sulfuric acid solution. That's a fraction. So I need to start with something that's a fraction. Now I want to put something on the bottom of the fraction that's going to be easy to turn into liters of H2SO4, and I want to put something on top that'll be easy to turn into moles of H2SO4. It'll be less work for me if I do that. In either case, I cannot put a fraction on top of a fraction. If I look at this, really what this means is moles of sodium hydroxide per liter of sodium hydroxide solution. So that's a fraction. I don't want to use this in either place. Let's look at the 3 numbers that we've got, and what is the most similar to liters of H2SO4? Well, I have 25 milliliters of H2SO4. It would be fairly easy for me to turn milliliters into liters. So I could write 1 milliliter of H2SO4 is 10 to the minus 3 liters of H2SO4, and I'd have the bottom part done. What about the top part? Remember, I have to put something up there that's not a fraction. So I'm not going to use the molarity here. I'm going to use the molarity as a conversion factor between liters and moles. I'm going to use milliliters of sodium hydroxide solution. Now notice something that is going to help me keep me from getting lost later. I am labeling these 2 volumes according to which substance I've got. And if I do that, I can make the units cancel out properly, and I can set up the problem pretty quickly. But take the extra time to write out which substance it is you're talking about. All right, so I need some way to convert milliliters of sodium hydroxide solution into moles of H2SO4. Now, in the last 3 videos, we said the first thing you do is look at whether or not you're converting one substance into a different substance. And that's exactly what you're doing here. So you need a mole-to-mole ratio. Now you've got moles of H2SO4 over here. If we drop moles of sodium hydroxide in here, our roadmap becomes this. Go from milliliters of this to moles, and then moles to moles. The moles to mole conversion factor is the critical link here. And our balanced chemical equation tells us that there are 2 moles of sodium hydroxide for every 1 mole of H2SO4. All right, what do I need to relate a volume of solution to moles of solute? The molarity. And I've got that. 0.100 moles of sodium hydroxide is 1 liter of sodium hydroxide solution. Well, that'll take me between liters and moles of sodium hydroxide. So I need something to go from milliliters to liters, and I know that. 1 milliliter is 10 to the minus 3 liters. All right, so here's my roadmap. Let's put it all together and make it into a calculation. All right. Let's get rid of the milliliters of sulfuric acid first. No, I'm going to have milliliters of sulfuric acid up here to get rid of it. And I know that 1 milliliter of that is 10 to the minus 3 liters. Now, be careful here, because usually we keep grinding on and on to cancel out the unit we got. But I don't want to cancel out liters of H2SO4 solution, because that's what I want to have on the bottom. So I'm done with the bottom part of this. So let's work on the top part. Now I've got milliliters of sodium hydroxide that I want to get rid of. All right, if I look here, I can go from milliliters to liters. Now notice right away that setting it up like this saves me some work in the long run, because there's a 10 to the minus 3 on top and a 10 to the minus 3 on bottom. And those are going to cancel, so I don't ever have to key them into my calculator. So now I have liters of sodium hydroxide at this point. I want to get rid of that. And we worked out that the next thing to do is go from liters to moles using the molarity. Okay, let's continue this down here. That gets rid of liters. Now I've got moles on top. That isn't what I want to end up with. So I'll put it on the bottom of the next conversion factor. And this is the part where I'm going from moles of NaOH to moles of H2SO4. 2 moles of sodium hydroxide react with 1 mole of H2SO4 for my balanced chemical equation. So now I can just do the math. So I have 10 over 25 times 0.1 divided by 2. So whatever that's going to be, all of my units cancel out except for moles of H2SO4. And liters of H2SO4 on the bottom. So this gives me the molarity of this. How many significant figures should I round my number, my final answer off to? Well, I have 3 here, 3 significant figures here, 3 significant figures here, and this is exact. So I would round that off to 3 significant figures. I would know the molarity of that unknown sulfuric acid solution out to 3 significant figures. Now, this calculation is not just a calculation. It is the basis for an experiment that we can do. We can actually execute this in real life and use it to find out the concentration of battery acid, say, in a battery, which is a practical sort of problem that you would want to know. But anytime I'm analyzing anything for an unknown concentration, I can use this technique. I just have to find a reaction that involves the unknown solution that I have, and I can do it this way. How would I do it experimentally? Well, I'm going to use a long tube that you've already seen. You used one of these in a lab already. It's called burette, remember? And it had a stopcock, a little spigot on the end of it. And it had marks on the side that told you how many milliliters you were dispensing. It started at 0 milliliters on the top, and it ran down to, like, say, 25 milliliters, something like that. Now what I'm going to do is put my sodium hydroxide solution in there. And I'm going to put my sulfuric acid solution down here. And I had 25 milliliters of this at this point. And what was my concentration of the sodium hydroxide solution? 0.1 molar in that problem we just did. So this is what it looks like at the start of the experiment that's based on the calculation that we just did. And you learned how to read a burette in lab. What I'm going to do is run sodium hydroxide solution down into the H2SO4, all the while mixing this. I might have this thing on top of a stirrer. And I'm going to run it down until the reaction is complete. There's no more sulfuric acid left. Now, how am I going to be able to tell whether or not the reaction is done? What I usually do with this particular titration is put a dye in there. And the dye will turn pink in the presence of excess sodium hydroxide. So if I add a little tiny bit too much sodium hydroxide, I'll see this turn from a clear solution to a pink solution. So what I'm going to do is dribble the sodium hydroxide solution down into here until I see the first appearance of a pink color. This is called an indicator. In this case, it's a dye, and the dye's name, you'll see it in problems and in experiments that you will do, is called phenolphthalein. And it changes from pink to clear. Now, when I dribble down enough so that I see the pink color, that tells me that I'm done. And we said what? It took 10 milliliters of that sodium hydroxide solution. Now I started it at 0 milliliters and I ran it down to 10, so 10 milliliters was dispensed. If I had started it out somewhere else, I could have taken the final volume minus the initial volume to get the volume that I had. Now this is called the end point. It's the volume of the solution you have in your burette needed to completely react. So here's a vocabulary word that I want you to know. They'll say the end point in the titration, and this whole thing is called a titration. This whole experiment that we're doing here. The end point is the volume of the stuff in the burette that you needed to completely to complete the reaction. Another vocabulary word is the stuff that we're analyzing for is called the analyte. It is the stuff that we're trying to find the molarity of. And here's another vocabulary word. They call the stuff that has known concentration that you load up into the burette the titrant. So the stuff in the titrant, in the burette, is the titrant. The stuff you're dribbling it into is usually the analyte. And the endpoint is the volume of that solution that you need. The indicator is the dye that you put in there that signals the end of the reaction. Know those 4 definitions.